Hello again. This is Karl Rittger representing Cold World Consulting, and along with ICIMOD SERVIR-HKH Himalaya Initiative and NASA SERVIR, I would like to welcome you to the second lecture in a series of 4 lectures that accompany our hands-on training each Monday and Wednesday morning. In the previous lecture that Rajesh shared, which hopefully you've all viewed by now, I talked about snow hydrology and remote sensing of snow extent with visible and near-infrared wavelengths, as well as remote sensing of snow volume with passive microwave wavelengths. Today, we'll talk about the energy balance of snow and the reconstruction of snow water equivalent. These two concepts are directly tied together as we use the energy balance, which can tell us about the volume of snow melted each hour or each day that we use to look at the past, and build up a snowpack as a sum of melted snow. However, first we'll do a quick review on concepts from the previous lecture. After discussing some basics about snow, I talked about the electromagnetic spectrum seen on the upper right here. We learned how, based on the Planck equation, the sun emits radiation because of its hot temperature at shorter wavelengths than compared to the Earth, shown to the left of the blue arrow. We learned that the atmosphere absorbs this radiation in various places of the electromagnetic spectrum, but in certain atmospheric windows, the atmosphere transfers much of the solar energy shown to the left of the green arrow. We learned about the multispectral sensors orbiting the Earth in their various orbits. These satellites measure visible and infrared wavelengths in some of the atmospheric windows where there is little to no absorption in visible and infrared wavelengths, circled in red. We talked about how these satellites don't measure continuously all the wavelengths, but rather in specific bands. We then learned about the special property of snow, which is that it's bright in the visible, which is why it appears white, and dark in the infrared wavelengths, as seen in the blue box on the right. Vegetation and soils have different spectral characteristics, as shown in the graphs on the lower right. There are several satellites measuring at these wavelengths at different spatial and temporal resolutions. Following our discussion on optical remote sensing, we discussed passive microwave remote sensing that relies on the microwave portion of the electromagnetic spectrum at much longer wavelengths and lower energies than the ones we discussed in the previous slide. Observations in these wavelengths are often discussed in frequencies instead of wavelengths. This technology requires coarser spatial resolution to collect enough energy. Passive microwave is used primarily to detect snow volume or snow water equivalent. Unlike optical remote sensing, microwaves move through the clouds and can be measured at night when the sun is not in the sky. The concept is based on the fact that shallow snow absorbs and scatters only some of the signal, while deeper snow absorbs and scatters more of the signal. Progress in remote sensing with passive microwave is being made to bring products to a higher spatial resolution, but there are still challenges in deep snowpack, forest, and areas with significant relief. The first lab that Timbo led you through on Monday morning used snow volume or snow water equivalent from the AMSR satellite that measures and uses passive microwave wavelengths. While these remote sensing techniques are useful, so are physically based models that estimate snow. In the first lab, we started work with a longer time series of data from a model called ERA5 that uses both physical modeling and data assimilation. Today, we'll talk through a physically based approach in estimating the energy balance of snow and reconstruction of snow water equivalent. The first thing to understand is that to melt snow, you first need to raise the temperature of the snow from some negative number to 0 degrees Celsius. The figure on the right is a conceptual figure that shows the temperature of snow on the x-axis and snow depth on the y-axis. The figure shows the effect of heating from the sun and cooling at night. On the bottom, you see that the snow is the coldest at the surface in the middle of the night, the red line. At 8 a.m., represented by the green line, the surface has warmed, but snow 1/10 of a meter deep is still cold. At 2 p.m., the upper 1/10 of a meter has warmed. By 8 p.m., when the sun is down, the surface temperature of the snow is back down to a chilly -10 degrees, but some of the deeper snow is still warm. At 2 a.m., all of that snow has cooled and you are back to the red line. So this is the diurnal cycle of snow in the winter. After the snow is at 0 degrees, you must melt the snow by overcoming the latent heat of fusion, the amount of energy it took to freeze the snow. Now that you've melted some snow, if the melt is going on the top layer of the snowpack, as we might see happen in these graphs, and snow is on the surface, it may refreeze as it moves through the snowpack because the deeper snow is cooler. Often, this is what will happen until the entire snowpack from top to bottom is at 0 degrees. The common term for this is a ripe snowpack or an isothermal snowpack, as it is all the same temperature, 0 degrees Celsius. To talk in more detail about bringing the snowpack to 0 degrees Celsius, we need to understand the specific heat, which is the amount of heat required to change the temperature of a unit of mass by 1 degree. The table in the red shows the specific heat for water, ice, and air. The units are joules per kilogram per Kelvin. It takes twice as much energy to raise water by a degree than it does ice. And furthermore, it takes half as much energy to raise air by 1 degree as it does ice. For those of you who aren't familiar, Kelvin is another scale to measure temperature. At 0 Kelvin, there is absolutely no molecular motion. 1 Kelvin is equal to 1 degree Celsius. To estimate how much energy to bring the entire snowpack to 0 degrees, also known as the cold content for a snowpack, we need to know the specific heat of ice, which in the previous slide we saw was 1.9 times 10 to the third joules per degree Kelvin. Next, we have rho s, which is the density of snow. The h here stands for height of the snow or snow depth. We didn't review it, but you saw in the first lecture, you'll remember that density times depth gives you the snow water equivalent, or SWE, the next two terms. If the snowpack is shallower or less dense, there is less ice, and thus it takes less energy to warm it to melting temperature. The final two terms in the equation are the temperature of the snowpack and the melting temperature of the snowpack, which is 273.15 Kelvin, or 0 degrees Celsius. After the snowpack reaches 0 degrees, all available energy can go into melting the snow. Melting the snow requires overcoming the latent heat of fusion, the same amount of energy it took to freeze the water. It's worth noting that the latent heat of fusion, or energy to freeze the snow, is 175 times larger than the specific heat of ice. So it takes a lot more energy to melt a kilogram of snow than it does to warm the snow to 0 degrees. To introduce where this energy comes from, we'll spend a lot of time talking about this conceptual diagram showing the various energy exchanges that take place between the snow and the atmosphere and the soil, before going over some equations to quantify the energy fluxes. Nearly all of the interactions of snow are with the atmosphere. As we'll see later in this lecture, the most important energy exchange in regions without significant vegetation is solar radiation on the left of the diagram here. Timbo or I may refer to this as shortwave radiation as well. The arrows next to each S indicate that there are two components, incoming and outgoing or reflected solar radiation. The amount of incoming solar radiation is dependent on the day of the year that controls how high the sun is in the sky, the Earth-Sun distance that changes through the seasons, as well as cloud cover. In the winter, the sun is low in the sky, and the result is a low amount of incoming solar radiation. As we move into the spring and then summer, the sun is higher in the sky, providing more incoming radiation at the surface. In the fall, the sun begins to become lower in the sky again. The Earth-Sun distance has some effect on incoming solar radiation, but clouds have more of an effect. Clouds, and in general the atmosphere, can absorb and scatter solar radiation, greatly reducing the incoming solar radiation. Some of the direct radiation from the sun becomes diffuse radiation. You can think of direct solar radiation as a beam of light coming from the sun, whereas diffuse radiation is emanating unevenly from the entire hemisphere overhead due to scattering in the atmosphere. So that's incoming solar radiation. The outgoing or reflected solar radiation depends on how large grains are of snow and how clean or dirty the snow is. As grains grow larger, the solar radiation must travel a longer length within each grain and more energy is absorbed and scattered. Larger grains absorb more energy in the near infrared and shortwave infrared than smaller grains. Dust, carbon, and other light-absorbing particles reduce the amount of visible solar radiation that is reflected as they absorb more of it. We'll go over this in some figures in a bit. Longwave radiation, on the other hand, the L's in this figure, is directly related to the temperature of the substance and its emissivity. Again, the up and down arrows next to the L indicate there is both incoming and outgoing or emitted longwave radiation. We touched on emissivity briefly in the first lecture, and it varies for different substances. Here, the snow in the atmosphere. Clouds in the atmosphere can modify emissivity. We'll talk about this more in a few slides. Turbulent fluxes are comprised of what's called sensible and latent heat. When temperature differences exist between the atmosphere and the snowpack surface, the potential exists for significant convective transfer of sensible heat to or from the snowpack, depending on the sign of the temperature difference, wind speed, surface roughness, and the stability of the air. When the air is warmer, during, for example, a hot spring or summer day, the snowpack can have large energy gains. In contrast, during the winter or at night, during the melt season, the snowpack can be warmer than the air, causing energy losses from the snowpack to the air. Water vapor exchanges between the snowpack and the atmosphere also occur. The transfer from the snowpack to the atmosphere is a loss of energy from either vaporization if there's a liquid, water, or sublimation when the snow skips the liquid state and goes straight to water. Conversely, the snowpack can gain energy from water vapor condensation as liquid or ice. Generally, during the cold winter, snowpack losses due to evaporation and sublimation. How much snow is lost to sublimation is an ongoing topic of research. In contrast, during melting periods and during rainfall, when the air has more moisture than the snow, condensation or sublimation on the snowpack occurs and the snowpack gains energy. Instead of temperature differences that control latent heat, it's vapor pressure differences that control sensible heat. Like latent heat exchange, sensible heat exchange is also related to surface roughness, wind speed, and atmospheric stability. Moving on, rainfall energy can influence the snowpack energy budget in three ways. First, relatively warm rain can add sensible heat. Second, the release of energy called the latent heat diffusion occurs if the snowpack is below zero and the rainfall refreezes. Thirdly, condensation can occur on the snowpack due to high humidity associated with rainy weather. Finally, we have ground heat conduction, which is relatively minor. In the winter, heat conducted from the soil can contribute to the gradual ripening of the base layers, but moving into spring is nearly insignificant. Once the snowpack is thin, say 20 to 25 centimeters, the ground warming becomes relatively more important. This is the mathematical representation of what I just talked about. First, we will go through each of these terms to describe them and discuss what each of the terms are important for or not important. Some of the variables here will look slightly different from what is in the lab, but the words and concepts are the same. The first term is the net shortwave radiant energy exchange, in short, net solar. This energy is from 0.4 microns or micrometers to 2 micrometers in the electromagnetic spectrum. As no surface can reflect all of the sun's radiation, net shortwave or net solar is greater than 0 during the day and 0 at night. To connect that with our previous lecture, here's a slide you've already seen. Looking at the yellow line in the upper right, recall that the sun's energy peaks at 0.5 micrometers. On the left is the graph that I discussed when talking about optical remote sensing and the shortwave and infrared spectrum, which is primarily solar radiation. To revisit another graph we've seen in the first lecture, It's the part of the electromagnetic spectrum in the black box here, a subset of what is used for optical remote sensing. To explain the electromagnetic spectrum a bit more, going on. In the black box, we see that the net shortwave radiation is the incoming solar radiation minus the outgoing or reflected solar radiation. Incoming solar radiation can be calculated for a clear sky using known quantities and geometry. There is a lot of detail in there, so I won't go into that in this lecture. For cloudy days, there are parameterizations that can be used to model, or it can be measured. Outgoing solar radiation is the incoming solar radiation times the albedo of the surface, in our case, snow. So we can estimate the net solar radiation if we know the incoming solar radiation and the snow albedo. Here are some examples of common substances and their albedo. Asphalt, for an example, has an albedo of 5 to 10% and therefore absorbs much of the sun's radiation. Crops and forests have an albedo of 10 to 25%. The Earth's average albedo is 31%. Fresh snow, on the other hand, has an albedo of 80 to 90%, but it can get darker. So let's talk more about snow albedo. Here I show the figures of snow with different grain sizes on the left, snow with different amounts of impurities in the center, and the combination of the two on the right. For all graphs, the x-axis is the wavelength and the y-axis is the spectral albedo or albedo at each wavelength. Fresh snow with a small grain size of 100 micrometers reflects the most energy from the sun and thus has the highest spectral albedo. Larger grains, which are older, represented by the blue line at the bottom on the left graph, have lower albedo because they absorb more energy in the near infrared part of the spectrum. We average or integrate for all wavelengths to get what's called the broadband albedo we use in the equation on the bottom of the last slide, also here. The center panel shows a single grain size with different amounts of light absorbing impurities like dust. The more impurities, the more the spectral albedo is lowered in the visible wavelengths. The graph on the right shows the combination of the impacts of larger grains and light absorbing impurities like dust. This graph shows some observations from a site in California called Mammoth Mountain. You'll work with some of this data in the lab. On the top right graph, the blue line represents the incoming solar radiation, and the green line represents reflected or outgoing solar radiation. The observations were taken over snow. The graph on the bottom shows the albedo, which was calculated by dividing the outgoing by the incoming solar radiation. You can see this actually changes hourly. The second term in our equation is the net long-wave radiant energy exchange, in short, net long-wave. This energy is from 2 micrometers to 100 micrometers in the electromagnetic spectrum. Going back to the electromagnetic spectrum, and these wavelengths in the black box that we didn't talk much about in the last lecture. They're longer than the visible and shortwave infrared, and shorter than the far infrared or microwave, where there is less energy. Again, referring to the graph on the right, the blue line is where the Earth is emitting with a surface temperature of 288 Kelvin, or about 15 degrees Celsius. The atmosphere is also emitting long-wave radiation, but its temperature varies from daytime when it's warm to nighttime when it's cold. Unlike solar radiation, incoming long-wave from the atmosphere and outgoing long-wave from the Earth occurs over a 24-hour period of the day. Long-wave radiation is governed by the Stefan-Boltzmann equation. Incoming radiation is shown on the right and is equal to the emissivity of the atmosphere times the Stefan-Boltzmann constant times the air temperature to the 4th power. Temperature here is in Kelvin. Similarly, the outgoing long-wave radiation is equal to the emissivity of the snow, which is near 1, times the Stefan-Boltzmann constant, times the snow temperature to the 4th power. The outgoing long-wave radiation also includes the small fraction of incoming long-wave radiation that's reflected. Together, the net solar and net long-wave are called all-wave radiation. During the melt season, in the daytime, net all-wave is usually positive, and the Earth and snow are heated, while at night, when the sun is down, the Earth is emitting more long-wave than the atmosphere. We'll return to this after we go through some more of the terms in the equation on the right. Together, these two terms are called the turbulent heat fluxes. In some models, because of the difficulty in accurately estimating wind speed and direction, surface roughness, and snowpack and atmospheric temperature, as well as vapor pressure, the two terms are combined and approximated as a simple function of temperature. Here, using H and L for sensible and latent heat, there are two conceptual models for estimating their quantity. For sensible heat, or H, the constants used include air density and the specific heat of air. For latent heat, or L, the constants used are air density and the latent heat, also known as the enthalpy of fusion, which we discussed earlier when talking about melting snow, and the latent heat of vaporization, or opposite of condensation, is the energy it takes to move water to a vapor. Both sets of equations are use some kind of description of the mixing. Sensible heat depends on a temperature difference, while latent heat depends on a vapor pressure difference. I'm showing you these conceptual equations because in the time we have, it would be difficult to understand every equation and every variable on the next two slides. As I noted earlier, when talking about the schematic on the lower right, sorry, that's on the lower left now, whenever temperature differences exist between the atmosphere and the snow surface, the potential exists for significant convective transfer of sensible heat to or from the snowpack, depending on the sign of the temperature difference, the wind speed, the surface roughness, and the stability of the air. Sensible heat exchanges can be positive or negative. Here is an equation we use to calculate the sensible heat. As I noted in the last slide, there's quite a bit going on here, and I've already left some of the detail out, so we'll move on. I also noted earlier, water vapor exchanges between the snowpack and the atmosphere also occur. The transfer from the snowpack to the atmosphere is a loss of energy from either vaporization if there's liquid water, or sublimation, which is when snow skips the liquid state and goes straight to water. I'm sorry, straight to vapor. Conversely, the snowpack can gain energy from water vapor condensation as liquid or ice. Latent heat exchanges can also be positive or negative. As with the previous equation, I previously described the conceptual model, so the equation is here for reference. The second to last term is the rainfall and sensible latent heat. As I noted when talking about the schematic on the lower left, rainfall energy can influence the snowpack energy budget in three ways. First, relatively warm rain can add sensible heat. Second, the release of energy called the latent heat of fusion occurs if the snowpack is below zero and the rainfall refreezes. Thirdly, condensation can occur on the snowpack due to high humidity associated with rainy weather. The energy depends on the rainfall intensity and the temperature of the rainfall, which is often assumed to be the temperature of the air. If the snow still has cold content, the energy will go into depleting the cold content before any melt occurs. Often in locations where there is snow, the air temperature is near 0 degrees and there is little impact. Rain on snow events are difficult to predict, but they can be very dangerous, causing flooding. Just to break up all the equations here for a moment, in 2017, after a large snow year, in the California Sierra Nevada, a warm storm persisted for 9 days, rapidly increasing the water in Lake Oroville, necessitating the activation of an emergency spillway, and it ended up damaging both the main and emergency spillway. The event was caused by what is called an atmospheric river, which are observed to be happening more frequently. The atmospheric river brought rain in February, which was catastrophic after falling on snow. The final term is ground heat conduction, which is relatively minor. As I noted earlier, in the winter, heat conducted from the soil can contribute to the gradual ripening of the base layers, but moving into spring is nearly insignificant. Once the snowpack is thin, say 20 to 25 centimeters, ground warming becomes relatively more important. So now I'm bringing together many of the components we went over in the previous slides. Mainly here, solar radiation or shortwave radiation, longwave radiation, and sensible and latent heat. The figure on the left here shows the hourly energy balance for a clear sky for a few days in May at an alpine site. You can see the solid red line, which is net solar, goes up to about 500 watts per meter squared during the day and down to 0 at night. The dashed red line is the net long wave and remains near negative 100 throughout this period. The solid blue line, sensible heat, is larger during the day when the temperature difference between the snow and the air are larger. The dashed blue line shows the latent heat, which remains slightly negative over the entire period. The key takeaway of this graph is that the black line, or the net solar flux, or what I've been calling the energy available from melt, nearly matches the solar radiation. On the right are some summaries of different locations showing energy fluxes over a day. The red bars show the net flux, and the yellow bars show the net solar radiation, with the other color bars showing the other energy components. The areas in the mid-latitudes with lots of sun, including the Alps, the Rocky Mountains, and the Himalaya, show that the energy balance is mainly driven by net solar radiation. Even near the poles in Greenland and Antarctica, solar radiation is the most important. So that was quite a bit about the energy balance. In the lab, you'll get to work with some real data, which will hopefully assist you in better understanding the energy balance. In the last lecture, I described how manual snow measurements are made either by digging a snow pit or by using a Mount Rose sampler or federal sampler, which can both estimate snow water equivalent. The problem with this is that those observations are single points, when we'd like to know how much water is an entire river basin. In a moment, I'll introduce a method called Reconstruction that allows us to estimate SWE using energy balance. We'll talk today about a concept of using the energy balance to reconstruct SWE. But in the next lecture, we'll learn a bit more about the energy balance over basins and the influence of topography and trees. First, today, I want to chat briefly about models and satellite observations of precipitation. Here's some recent work on gridded temperature and precipitation in the North-Western Himalaya done in 2020 with the publication shown on the bottom. The points on this map show the locations of 19 snow and avalanche study establishments. The authors of this paper compared 7 different gridded precipitation data sets on the left for 3 different sites, and on the right, 5 different gridded temperature data sets to the observations I showed on the last slide. Without going into the detail of what each subplot is showing here, the left, though, are precipitation and the right are temperature, you can easily see that there are significant differences in both precipitation and temperature between the 7 gridded precipitation data sets and the 5 gridded temperature data sets. The uncertainty in these products is why we use Reconstruction that I'll describe in a few slides. One of the products here is ERA interim, a precursor to ERA 5 that you used in Lab 1. In addition to the absolute values of the 7 precipitation products, the authors looked at trends in precipitation. The trends vary in magnitude as well as sign. Again, this is why we use the Reconstruction with the Earth energy balance of snow. So instead of relying on these uncertain precipitation products, we use an energy balance Reconstruction model to estimate the amount of water in the snowpack or SWE retrospectively. Rather than relying on uncertain gridded estimates of precipitation, the idea here is that the SWE at time n equals the initial SWE times 0, labeled SWE 0 minus melt from day 1 to n. If we wait until all of the snow melts so that SWE n equals 0, we can rearrange the equation to get the initial or maximum SWE is the sum of all of the melt. The melt can be calculated using radiation balance, which I described in all of the previous slides. To help you understand, I've plotted the measurements of SWE from a number of snow pillow sensors that I showed in the first lecture. SWE n is on the right side when all the snow is gone. We work backwards in using the energy balance to estimate how much energy is available to melt the snow. And we repeat that every day until a date when the maximum occurred. We now convert that amount of energy to a melt amount and sum that to get the total SWE 0. This model is valid from the maximum accumulation through the day snow melts. In summary, the energy balance consists of solar and long-wave radiation, which comprise all-wave radiation, sensible and latent heat, which comprises the turbulent fluxes, and the ground heat flux if we ignore rain on snow. In the alpine environment, like much of the Hindu Kush Himalaya, the energy balance is primarily driven by solar radiation. We also learned that absorbed solar radiation is dependent on the snow albedo. Snow albedo decreases as snow ages and grains get larger, and with the addition of light-absorbing impurities such as dust, carbon, or litter. Long-wave radiation energy balance is generally negative. Sensible and latent heat can be estimated if you know the temperature, vapor pressure, and wind speed direction, but can also be simplified as a function of temperature. Ground heating is somewhat negligible, especially for deep snowpacks. The summary of Reconstruction. The reason we do Reconstruction is because it does not depend on uncertain precipitation estimates from either rain gauges, which are points, or reanalysis, spatially distributed data. We estimate the SWE and the melt with the snow energy balance. The Reconstruction is performed only retrospectively and sums the melt for each day. It reconstructs SWE starting at the snow disappearance date and working backwards in time. And it can accurately estimate the snowpack from maximum accumulation through the snow disappearance date. That's all I have for now. And I and the others from Cold World Consulting will be available for questions in the hands-on portion of the training. Bye for now, and thank you.